Hi and welcome. In this video, we're going to introduce the concept of inverse functions. So I want to start by reminding us about what a function is with its definition specifically. So a function is a relation that is going to take in a single input and then tell us exactly one corresponding output. So we should be able to give a function an input and it knows exactly which output to provide us. So just to illustrate this, I can have my function f. It's taking in this set of inputs, and then it maps those inputs to another set of outputs. So the inputs are the domain of our function f, and those outputs are the range of the function f. We also might write this as f of x equals y. So the function takes in an x and provides out a y. Now, what we want to be able to do is to reverse this process. So if we've applied a function, we want to be able to undo that function, and that's where our concept of inverse function comes in. So we say that an inverse function of a function f takes in an output and tells you which input it came from. So if we've applied the function f, it's going to then take those outputs and tell us which inputs got mapped to them. So if we were to write this, we might write that we have f inverse. Notationally, we're going to use this little -1. This is the inverse symbol. It can also be an exponent in a different setting, but here we're using it as the inverse. So this is to indicate that we're undoing the function f. We have f inverse. And what it does is it takes the outputs of the original function f, and it uses those as the inputs. So it starts with the outputs of the previous function, and then it tells you which input it came from. So it maps to the set of inputs. So we're basically reversing the process. We're starting with the outputs of the original function. Those are our new inputs. And then they get mapped to the inputs of the original function, our new outputs. So the inputs to the inverse function, or the domain, are the outputs of the function f. And the outputs, or the range of the inverse function, are the inputs of the function f. So here we might write that f inverse of y equals x. So the inverse function takes in an output value y, and provides us the corresponding input value x. So I know this is a lot of vocabulary, a lot of words. Let me write this out in a couple more summarizing statements, and we'll go over a few more things to hopefully solidify this. So here, the domain of the inverse function is the range of the original function. So what we're doing is we're taking the inputs for the inverse function as the outputs of the original. Then similarly, we can say the range of the inverse function is the domain of the original function. So the outputs of the inverse are exactly the inputs of the original function. So this is a lot of words just to say that if we have a function f, we give it an input, it provides an output. The inverse does the opposite. It takes one of those outputs and tells us which input it came from. Alright, so let me show you an example with some tables briefly, just to show you what this looks like with the inverse function. So let's say we have a function f and a function g. So they have some inputs and corresponding outputs. And then let's answer the following questions with the inverse. So let's find f inverse of -4, f inverse of 0, f inverse of 5, and then we'll also find g inverse of -3, g inverse of 0, and g inverse of 5. So what's happening here is that the inverse function takes in an output, and we want to find out which input it came from. So starting with f inverse, all of the inputs to f inverse are in the right-hand column of the table. They're the outputs of the original function. So when we do f inverse of -4, we're looking for -4 as an output, or an f of x value. Then we want to know which input it came from. I see that it came from the input of x equals 2. So we would say that f inverse of -4 is equal to 2. Okay, we repeat this for f inverse of 0. F inverse of 0 is saying which input gives me an output of 0 in my original function f. So 0 is an output of our original function. I look at which input it came from. I see that it came from the input of -3. So f inverse of 0 is -3. Then lastly, we have f inverse of 5. So f inverse of 5 is asking which input gives us an output of 5. So here 5 is an output value. However, when I look in the column of outputs, I don't see this as an option. So this actually isn't an output, and so we would say this solution does not exist. There's no input that gives us an output of 5. 5 is an input value, but that's not what this is asking. This is saying which input gives me an output of 5. Let's repeat this for the function g. So first we have g inverse of -3. This is saying which input gives me an output of -3. I see that -3 corresponds to an input of 3, and so the solution is 3. Then for g inverse of 0, this is saying which input gives me an output of 0. So I see that 0 has an input of -1, so -1 is my solution. Then lastly, we have g inverse of 5. This is saying which input gives me an output of 5. Now, this is where things get a little odd. I'm noticing that 5 shows up twice as an output. So the input of -4 corresponds to the output of 5, and the input of 0 corresponds to an output of 5. So I have a hard time answering this question. I'm not sure which to pick. I could say that it's -4 or 0, but what we want to be able to do when we're talking about an inverse is know exactly which input it came from. So what this is telling me is that g inverse isn't actually a function, because I gave g inverse a value, I gave it 5, and we didn't know which output to provide. So this is going to be something we want to fix. Just like we want every input to have exactly one output of a function, we want this to also work for the inverse. So let's talk through what it would mean for the inverse to also be a function. So this means that in order for the inverse to represent a function, each of its inputs must have exactly one output. But there's something a little confusing happening here, because the inputs and outputs of the inverse are related to the inputs and outputs of the original function. So this is actually saying that each output of f, since those are the inputs to the inverse function, needs to have exactly one input of f, since those inputs of f are actually the outputs of our inverse function. So this tells us that in order for f inverse to represent a function, each output of f, the original, needs to have one corresponding input. So we saw this in our example. The output of 5 had 2 corresponding inputs for the original function, and that was confusing because we didn't know which solution to pick. So we want each output to have only one input that goes with it for the original function in order to make the inverse work well. So we give this concept a name. Specifically, we say that a function f is 1-to-1 if every input corresponds to only one output, and if every output corresponds to only one input. So it's 1-to-1 in that input is one output, output is one input. So in our vending machine example or analogy, this means that every input or number you type into the vending machine needs to provide one item only. You want to know which item you're going to get when you type in the number. But if you come show me that you got a specific candy bar from the vending machine, I should be able to tell exactly which input you must have given the vending machine. So that's 1-to-1. Every output, so every item, needs to appear only once so that I can tell you exactly which input it came from. This ensures that both f and its inverse are functions. So we would say that if a function f is 1-to-1, meaning it has this quality here where every input has one output and every output has one input, then the inverse, f inverse, is also a function. What this tells us is that 1-to-1 functions must pass a vertical line test and a horizontal line test. So the vertical line test told us that every input has one output, but now we can repeat this horizontally, where every output must have only one input. Alright, so let's go back to our examples and use our new vocabulary. So when we look at the functions f and g, I'm first noticing that these really are functions. Every input to f has only one output, and every input to g also has only one output. So f and g are both functions. Now let's check if they're 1-to-1. So what we do is we check the outputs, and we want to make sure every output shows up only once, meaning it only has one input that corresponds to it. So here, all of the outputs of f only have one input, and so this works. This is 1 to 1. So f is 1 to 1, meaning that every output has only one input. But then when we look at g and we look at the outputs, we see that the output of 5 has multiple inputs. So this is not a 1 to 1 function. So the output 5 has two inputs, both -4 and 0, so g is not 1 to 1. It's still a function, it's just not 1 to 1, and this is going to affect the inverse. So because f is a 1 to 1 function, we would say that f inverse is well defined, meaning everything is going to work out well, and it is also a function itself. So the function f and its inverse are both functions. But for g inverse is not well defined because it doesn't have this property of being 1 to 1, and it's not a function. So this is because that output of 5 for the original function had two inputs. So g inverse is not going to work in the way we want it to. It's not well defined and it's not a function. So one more thing you can do to try to make sense of this is to make a table for the inverse. So when we're being asked if the inverse is a function or not, what we can do is make a table that represents it based on the original function. We can think of the f of x as a y value, and then what we're going to do is just swap the x and the y, or the input and the output, to make the inverse. So our new table has the inputs and the outputs switched. So I'm starting with a y value, and the inverse function gives a corresponding output for it, or an x value. So if I have my original function, x, f of x, my new table for the inverse is going to be y, f inverse of y. Then we can do the same thing for g. We're just going to make our new table and swap the inputs and the outputs. To make this simple, you could just label them as xy and yx, but I'm trying to really be careful here with the function notation. So now we can look at our new tables for the inverses. For f inverse, I'm seeing that all of the inputs have only one output, meaning that f inverse is a function. But when we look at the table for g inverse, we see that some of the inputs have multiple outputs. So the input of 5 has two outputs, meaning g inverse is not a function. So what you can do is just swap these inputs and outputs and then use your normal way of checking whether something is a function or not by looking to see if every input has only one output. Alright, so that's an introduction to inverse functions. Thanks so much for watching, and I will talk to you in the next one.